Hello everyone, I'm Naveen and alongside me are Nina, Andrew and Kumanan. We are part of Team 1 and we will be taking you through the preliminary urban air mobility system safety analysis of Joby Aviation's Joby S4. So for the safety analysis, we will walk you through first at the aircraft level, then for the system level safety analysis, we will take you through Joby's propulsion system to be more specific. So first, let's start with the vehicle description. So our vehicle of choice is Joby Aviation's Joby S4, particularly its production prototype because that is the one that is closest to certification. And as we know, it's an all-electric eVTOL configuration, and this is primarily intended to operate in urban regions. And this is a multiple tilt rotor configuration which has six propellers, four on its wing and two on its tail. All six propellers are completely tiltable to forward flight mode, but the tilting mechanism is slightly different between the ones on the wing and the as compared to the ones on the tail. And it is also completely capable of performing an autonomous flight as well as a piloted flight. And since it is all electric, it has really low noise footprint, and it also has like compact footprint in general, which is quite helpful to think about it because since it's operated primarily in urban regions, it can operate quite well in limited parking spaces or limited recharging spaces. Now let's take a look at some of the safety features of our vehicle. So Joby's distributed electric propulsion system is central to its safety architecture, and each motor here is powered by two separate inverters, and each inverter is wired to a separate battery pack so that if one of the inverter fails, the motor will still continue its function because the other inverter, which is connected to a different battery pack, will still power the motor. And we also have like four isolated and redundant battery packs, and they are placed away from the passengers in the wing so that it is also adding additional safety feature to our vehicle. So these battery packs that we have are like capable of having like to perform long range missions with fast charging capability, and also has like a long operating lifetime so that we don't have to replace the battery quite often. And overall it has like quite high level of redundancy. This entire aircraft can perform the mission safely with complete loss of one of the propeller, but if there is more than one propeller loss, that would depend on the flight segment, how much safety critical it is. But overall this design has like no single point of failure all across the aircraft system. So here are some more key features of Joby S4. Since noise and certification are some of the major considerations for any urban air mobility, looking at some of the noise levels of Joby S4, we can see that it is 100x quieter as compared to typical aircraft at takeoff and landing, and it is almost silent when it is on its cruise flight, which makes sense because Joby is intended to primarily operate in urban regions where noise levels can be like pretty significant. And Joby is on its way to certification. It had already signed the G1 agreement with FAA. So it is primarily targeting for Part 23 certification because 85% of it has like typical aircraft requirements with some special considerations for 15%, especially for the battery with its all electric nature and vertical takeoff and landing capability, and also it being like fully autonomous. And on the right, we do see like more description of Joby's features with four passenger capacity and one pilot capacity. And something to note here is the structures in which it has a V-tail and a tricycle wheel landing gear, which is non-retractable. So something interesting is that it used to be retractable until the pre-production prototype, but when it comes to the production prototype, they decided to go with a non-retractable configuration because that reduces the complexity further. So that brings us to our overall problem description and scoping. Since Joby is planning to have high frequency operations over densely populated urban areas, which are constrained by a lot of factors like noise, airspace, and limited infrastructure capability, so it is of utmost importance for us to look into its safety features and do a detailed safety assessment. While Joby is making significant progress towards safety and certification, the issue is there is only limited public analysis on how these traditional safety frameworks like ARP 4754 or 4761 can be applied to such novel aircraft configuration. So our goal here is to do a preliminary safety assessment of Joby S4 and see how these traditional safety standards can be applied at both vehicle level as well as a propulsion system level towards this novel aircraft concept, especially the distributed electric propulsion system, because that is quite critical in providing thrust and lift throughout all flight phases. Next, here's the operational concept for our vehicle, which is basically its mission profile showing Joby flying over Metro Atlanta. Oh hey, look, there's a tech tower in there. And this ConOps basically outlines all flight phases starting from taxi out all the way to landing and taxi in. And something important to note here is that it can perform its mission either through a completely wingless flight with a eVTOL configuration, or it can transition to a forward flight and perform its mission using a powered lift as well. Next, we have this physical architecture representation of our aircraft at the vehicle level using this block diagram. So it basically helps us break down the aircraft into multiple subsystems like structure, propulsion, etc., and how each subsystem is connected to the aircraft and what are the components that goes into each subsystem. For example, we can see that in structures we have airframe, wing, nacelle, and other actuators, etc. And for propulsion system, which will be of our main focus for the later part of the slides, shows that it has multiple electric motors, inverters, propellers, and also like force vectoring mechanism and health monitoring mechanism in it. Since we have a good idea about our vehicle now, our next step is to conduct a preliminary safety analysis at the aircraft level. So one of the key elements of performing a preliminary safety analysis is performing a functional hazard assessment. FHA is basically a structured approach. It helps us identify different failure conditions that are associated with different aircraft level functions. And to do that, first we need to have a functional decomposition of our aircraft. So we have 9 different identified functions like provide aerodynamic performance, support navcom, maintain energy source, maintain environmental comfort, etc. And once we have identified this function, it will help us determine different failure condition associated with each of this function, which can further help us classify whether that failure condition is going to be of what likelihood or what severity and different like target levels of safety, etc. So this is how a typical FHA looks like. Shown here is an FHA for one of our functions, provide thrust or propulsion capability, and we can see that it has multiple failure conditions like a complete loss of thrust, partial loss of thrust, or incorrect thrust, etc. And depending on the flight phase we are considering, the same failure condition can have different failure effect and different severity classification. So for example, we can see that the partial loss of thrust is hazardous if we are considering the takeoff or landing phase, but it is just a major severity when we are considering a cruise phase. And depending on the severity classification, we are assigning a particular likelihood for it to happen, like whether it is extremely improbable or extremely remote, etc. And this will lead to a particular target level of safety and development assurance level. And we have repeated this process for all the identified functions, but due to time constraint, this is the only thing that we will be showing in this presentation. Here are some more details about development assurance levels and target level of safety that we saw in the FHA. So development assurance is basically a process of establishing different confidence levels for each of the failure condition that we identify. And the target level of safety is basically how often it is acceptable to happen provided the amount of flight hours. So for example, when we classify something as catastrophic severity, it has a development assurance level of A, which means it can lead to a complete loss of aircraft or cause multiple fatalities. So the probability of that happening should be as low as possible, which is extremely improbable. And to quantify that, it can be said that it should happen less than 1 in a billion flight hours. So once we have the FHA performed on all the identified functions, here we can sum it up using this aircraft level risk matrix. It basically maps the severity against its likelihood, and we can see that when a failure condition falls in a green zone, it is acceptable, but if it is in yellow zone, it is tolerable, but we need to have some mitigation strategy, and it is highly unacceptable if it is falling in any of the red zone. So none of our failure conditions are in the high risk zone right now, because this is the targeted level of safety that we want, rather than the conceptual estimates. And once we have a failure condition that is falling in the high risk zone, we have two options. Either we can bring it down by reducing the likelihood of its happening, or reduce the severity and move it to the left. So that brings us to the final element of our preliminary vehicle level safety assessment, which is a fault tree analysis. So FTA is a deductive top-down approach which helps us understand the root causes of each of the failure conditions, or we call it as an undecided event. For each of these undecided event to happen, we look into some of its immediate causes, contributing factors, and each of their associated probabilities as well. So all of them are connected using logic gates, either using AND or OR, and this FTA overall helps us set a particular target level of safety for each of the undecided event by setting different target level of safety for each of those causes or the contributing factors. So for our vehicle level FTA, we have considered three FTAs: a loss of thrust, complete loss of navigation function, complete loss of communication function. And for the system level FTA later, we will be going in depth into one of these function, which is loss of thrust, for which the vehicle level FTA is shown here. So the undecided event of focus is loss of thrust, for which the target level of safety is 1 in a billion flight hours. So some of the primary causes for this undecided event would be either it can happen due to loss of energy supply, or damage to rotor carrying structures, which means the wing itself had broken, or loss of control authority, or prop rotor failure. And each of these primary causes also has its own target level of safety, which when combined together gives the target level of safety for the undecided event. And since these primary causes are mutually exclusive, we are combining them using logic OR gate. And the same process can also be repeated for any of the primary causes as well, with its own contributing factors. Like the loss of energy supply can happen either due to battery failure, or inverter failure, or power distribution failure. Similarly, we can decompose each of this subsystem into multiple levels until we reach a particular component level of safety that we want. And this process is repeated for all the FTAs that was mentioned, and this concludes the final preliminary vehicle level safety analysis. And next I will let Nina talk more about the system level safety analysis. Thank you.
Now that we've introduced the Joby S4 aircraft at the vehicle level, we're narrowing our focus to one of its most safety-critical systems, that's the propulsion system. We chose the system as the target of our safety analysis because it's central to the aircraft's performance and operations. For an eVTOL to operate safely in dense urban areas, it needs to take off and land vertically, transition to forward flight, and do so reliably multiple times per day. The propulsion system is the main part, and it's what enables this entire mission profile. It also represents a novel design compared to traditional aircraft, so it offers new benefits, but also new safety questions. We wanted to understand, how well does the system work? What if it fails? What happens if we lose just one motor mid-transition? That's why we applied the safety assessment to the entire system. Joby uses a distributed electric propulsion system. That means it has multiple independent electric propulsion units. This design eliminates any single points of failure, reduces maintenance complexity and costs, and improves the overall acoustic performance due to the use of smaller, quieter motors. The DEP system is built around 4 core features. The first one being it's a multi-unit electric propulsion system, so multiple motors share the load and thrust, ensuring redundancy. It has a energy-based powertrain, so the energy comes from onboard batteries, which is then converted into mechanical power. It has thrust vectoring that precisely directs thrust for smoother maneuvering, and an integrated control loop that responds dynamically to pilot inputs and environmental conditions. These features work together to enable a stable VTOL and cruise flight. The table here shows some other hardware and software components involved in the system. This is a functional block diagram that illustrates the key functional flow of the entire propulsion system. Starting from the batteries, that's where the energy is stored and used to power the thermal management as well as the inverters. The thermal management system is used to monitor the health and temperature of the entire system, ensuring proper, safe operation of the entire aircraft under various conditions. The inverter and wires, on the other hand, they convert and transmit the power to the motor that generates the mechanical power needed to rotate the propellers. Then thrust is generated and vectored for better maneuvering, and all of this is part of a closed loop that responds to the pilot inputs and flight conditions. Another function of the propulsion system is to maintain structural integrity. This diagram maps the different physical locations of the propulsion elements on the Joby airframe. Propulsion units are distributed across the left and right wing and the tail. It has 6 propellers, each of them connected to a dual wound motor. Each motor is redundant and powered by 2 separate inverters, and each inverter connected to a separate battery pack. So there's 4 battery packs in total, which are placed in the wing away from passengers. So this entire layout has high levels of redundancy, and even with one inverter or battery pack failure, the motor still would continue to function. Moving into the system safety analysis, we performed a preliminary system safety assessment using the ARP frameworks. Similar to the vehicle level, we conducted a system-level functional hazard assessment by decomposing the propulsion system into its 6 key functions, that is, generate mechanical power from stored energy, convert the mechanical power to aerodynamic force, control force vectoring, respond to inputs, ensure structural integrity, and monitor system health. For each function, we identify potential failure conditions, their effects, the flight phases they were associated with, and assess their severity and likelihood. For example, for the function respond to control inputs, we identify one of the failure conditions to be no response to a control input. This is applicable to all flight phases and would lead to the pilot losing control of the entire aircraft. This would result in a crash leading to the loss of the vehicle and its occupants, and this is very catastrophic and extremely improbable. Another example for the function monitor propulsion system health, we identified a failure condition to be false propulsion fault indication. So in all phases, this would just add on unnecessary maintenance or emergency actions, increasing pilot workload. Since there's no loss of life or injury, this wouldn't be classified as catastrophic or hazardous, but just major and with a remote likelihood. We then created a system-level risk matrix to visualize how these functional failures map in terms of severity versus likelihood. This helps identify which hazards need design mitigations. It is important to realize that these functions aren't isolated. A failure in function 1, like poor power generation, can cascade into functions 2, 3, and 6. For example, if a motor fails to generate power, it also affects the aircraft's ability to vector thrust and maintain control. So even though we list these functions separately in the FHA, in the real system, they are tightly coupled. And that's why we also track failure propagation in later analyses like FTA and bow tie. To deepen our understanding, we constructed a system-level fault tree analysis to analyze one of the failure conditions, that is, partial loss of thrust or lift. This FTA identifies combinations of failures that could lead to unsafe conditions, as well as the probability of it. Partial loss of thrust could happen due to the failure of any one of the propellers. That propeller could fail due to motor issues, power issues, blade damage, tilt mechanism failure, or incorrect command. These root causes are further decomposed into component-level causes, allowing us to trace failure and evaluate which subsystems need more redundancy, isolation, or monitoring. We also created a bow tie diagram to visualize how threats propagate from system-level faults to vehicle-level consequences. For example, threats like motor health degradation would result in a complete loss of thrust. Preventative barriers such as thrust allocation checks, battery oversight, or motor health checks can reduce the chance of these threats becoming a hazard. If a hazard occurs, emergency responses like envelope protection, emergency landing mode, or motor shutdown procedures can help mitigate the consequences of a crash or loss of control. This view helps bridge technical faults and operational risks. To summarize, we applied the traditional safety frameworks like ARP 4754 and 4761 to this Joby aircraft. We were able to recognize multiple novel failure modes due to the integration of electric systems, multiple propulsion units, and advanced control system. We were able to conclude that the built-in redundancy and fault-tolerant design that Joby has make this propulsion system well aligned with safety objectives. Although we believe that novel concepts like these could benefit from an improved framework for thorough assessment of system safety. For Joby and similar aircraft, real-time operational data could be used to build probabilistic models of failure evolution over time, something that traditional FHA doesn't fully capture. That's where newer methods like continuous FHA or Bayesian safety analysis might be useful, especially when trying to certify aircraft with highly novel architectures but limited historical failure data. This would allow for modeling of failure severity along a continuous spectrum, providing a more realistic and robust assessment of risk. That's it from Group 1. Thanks for listening.